Hey everyone, welcome back. Ready for another deep dive?
Always.
Awesome. Today, we're tackling the data link layer.
The data link layer.
Right. You know, it's the unsung hero behind all that seamless streaming and downloading we all love.
It really is.
I like to think of it as the delivery truck driver of the internet. You know, making sure your data packets reach their destination safe and sound.
That's a great analogy. It's all about bridging that gap between the world of network addresses and actually sending signals across, wires or wirelessly.
Speaking of bridges, where does this data link layer fit in the whole network picture? Think about the TCP/IP model, right?
Yeah.
That layered architecture of how networks communicate. We've talked about that before.
Absolutely. The data link layer sits right above the physical layer.
The physical layer, so that's dealing with the raw signals, right?
Exactly. Those electrical signals or light pulses traveling through cables or, wirelessly.
So, to put it simply, the physical layer is like the infrastructure, the roads and bridges. And the data link layer is like the traffic cop, directing the flow of data.
Perfect analogy. The data link layer takes those raw signals from the physical layer and gives them structure and meaning.
So it's not just a jumbled mess of bits and bytes flying around.
Nope, not at all. It transforms those signals into organized units called frames.
Frames. Okay, so what are those?
Think of a frame like an envelope for your data.
An envelope. I like that. So it's packaging the data up neatly.
Exactly. And inside each frame, you have the data you're sending plus important info in the header, like the addresses of the sender and receiver.
The addresses. So that's how devices on the same network can find and talk to each other.
Precisely. It's all about making sure the right data gets to the right place.
Okay, that makes sense. So if I'm sending, say, a picture to my friend across the internet, does it go through multiple envelopes, like one at the data link layer, then a bigger one at the network layer, and so on?
You got it. It's like a super efficient postal service.
Wow. So each layer of the TCP/IP model repackages the data with the information it needs.
Right, so at the transport layer, you have segments. Those become datagrams at the network layer. And finally, frames at our data link layer.
That's fascinating. Speaking of data traveling efficiently, I was looking through the Computer Networks textbook, and there's this section on Wi-Fi speeds that caught my eye. Do you remember 802.101?
Oh yeah, 802.11n. That was a big step forward.
It was. The book says it could reach speeds up to 450 Mbps.
Impressive speeds for the time.
It used wider frequency bands and could even have up to 4 antennas.
4 antennas, wow, that really boosted performance.
Why was that such a game changer for us regular users? 450 Mbps sounds pretty fast already.
It was a game changer. Think about it. Smooth HD video streaming, faster downloads of large files, even online gaming became way more responsive.
Oh, right. I remember when things finally stopped buffering all the time.
Exactly. This really shows how much we're always pushing for faster and better wireless communication.
And we all benefit from that every day. But there's a catch, right? I read that wireless communication, because it's a broadcast medium, can be prone to collisions.
That's right.
Like everyone trying to talk at the same time in a crowded room. Is that a good way to put it?
Perfect analogy. And to handle that potential chaos, 802.11 uses a method called CSMA.
CSMA, so what's that stand for?
Carrier sense, multiple access. Basically, devices listen before they transmit, waiting for a quiet moment to send their data.
So it's all about being polite and taking turns, even for data packets.
Exactly. It's like having good network etiquette. And here's a fun fact. This whole idea of listen before you talk actually comes from an earlier wireless network called Aloha. It was developed in Hawaii.
Wow, seriously. So modern Wi-Fi has Hawaiian roots.
It does.
That's incredible. But tell me, how does the CSMA thing affect me when I'm, say, browsing the web at a busy coffee shop? Does it actually make a difference?
Absolutely. It's the reason you can usually have a stable Wi-Fi experience even when a lot of devices are competing for bandwidth.
So that's why my connection doesn't completely die when the coffee shop is packed.
Exactly. But sometimes all that politeness can also lead to slightly slower speeds.
So that explains those occasional lags.
It's always a balancing act between reliability and speed.
Makes sense. Okay, so we have these frames being politely passed around, but how are they structured? I was reading Data and Computer Communications, and it goes into the nitty-gritty of frame structure. It's not just data stuffed in an envelope, right? There's a specific format.
You're right. A frame is very organized. Think of it this way. You have the header, that's like the address and return address on your envelope.
Okay, so that's for the sender and receiver information.
Exactly. Then you have the data payload, which is the actual message you're sending, of the letter inside the envelope.
Right, the actual content.
And finally, there's a trailer at the end, which often includes an error checking code.
Error checking, like making sure the data arrived in one piece.
Precisely. It's like adding bubble wrap to protect your package. But there's another clever trick they use called bit stuffing.
Bit stuffing. What's that?
So there's a specific sequence of bits, 0, 1, 1, 1, 1, 1, 10, that signals the end of a frame.
Okay, I see.
But what happens if that same sequence randomly appears within the data you're sending?
Oh, that could cause some confusion, right? Like accidentally ending your sentence too soon.
Exactly. That's where bit stuffing comes in. If the sender sees 5 1 bits in a row, it adds an extra 0 bit. This prevents that end-of-frame sequence from appearing in the data and confusing the receiver.
So it's like a special marker to prevent false endings. That's clever. But why go through all that trouble? What's the big deal if the receiver gets a bit confused?
Well, this is all about ensuring reliable data transmission.
Reliable transmission, so that's the key.
It is. It prevents the receiver from mistaking part of the data for the end of the frame.
Which could lead to all sorts of problems.
Exactly. Imagine downloading a file and it's suddenly cut off because the receiver thought the frame ended too early.
Oh, that would be frustrating.
Bit stuffing prevents that from happening. It's all about making sure your data arrives safely.
It's like a quality control check built right into the system.
Exactly.
Okay, that makes a lot of sense. Now let's talk about the different types of services the data link layer offers. Data and computer communications mentions 3 main types. Can we break those down and see how they affect us as users?
Absolutely. Let's dive into the world of data link layer services. So you want to know about these different data link layer services. Well, think of it this way. Sometimes you just need to send a quick message, and sometimes you need a guaranteed delivery, like with a signature confirmation. The data link layer offers different services to handle those different needs.
Okay, I like that analogy. So what are these different levels of service, and how do they affect, me as a user?
Let's start with the simplest one, shall we? It's called the unacknowledged connectionless service.
Unacknowledged connectionless. That doesn't sound very reliable.
Well, think of it like sending a postcard. You drop it in the mailbox, and you hope for the best.
Oh, okay, I see.
There's no guarantee it'll arrive, and the receiver doesn't send anything back to confirm they got it.
That sounds kind of risky. Why would anyone use that kind of service?
It's good for applications where it's okay if some data gets lost. Things where occasional data loss doesn't really matter.
Can you give me an example?
Sure. Imagine a sensor sending temperature readings. If one reading gets lost, it's not a big deal. The next one will come along soon enough, and you'll still get the general idea of the temperature trends.
Okay, that makes sense. So it's about choosing the right tool for the job. What about the second type of service?
That's called the acknowledged connectionless service. It's a step up in reliability.
Okay, so how does it work?
In this case, the receiver sends back an acknowledgement to say, hey, I got your frame.
Oh, so there's at least some confirmation this time.
Exactly. It's like sending a letter with delivery confirmation. You know it got there, but you're not having a whole back and forth conversation.
Right. When would you use this kind of service?
It's good for things where some data loss is okay, but you still want some basic assurance.
I can't really think of an example. What comes to mind for you?
Well, online gaming, for instance. If a few packets get lost here and there, it might cause a little glitch, but it won't ruin the entire game.
That's a good one. As long as most of the data gets through, you're good.
Exactly. Now, the third type, the acknowledged connection-oriented service, that's the most reliable of the bunch.
Acknowledged connection-oriented. Okay, what makes it so reliable?
It's like making a phone call. You set up a dedicated connection before sending any data, and every single frame is acknowledged.
So it's like a direct, secure line for your data.
You got it. It guarantees the highest level of reliability and data integrity.
That sounds like what you'd want for something really important.
Exactly. Think about transferring a large file or having a video call.
Right. You wouldn't want any interruptions or lost data there.
Exactly. Those applications need high reliability. Imagine your important files getting corrupted or your video call dropping in the middle of an important meeting.
No, thank you. I think I prefer reliable connections. It's amazing how the data link layer offers all these different options to fit our needs.
It is. It's all about flexibility and choosing the right service for the job.
But you mentioned earlier that even with all these mechanisms in place, errors can still happen. What happens if, say, a bit gets flipped during transmission, even with these services?
That's a great question. That's where error detection and correction come in. The data link layer has some clever ways to make sure your data arrives exactly as it was sent.
Clever ways, huh? Tell me more.
One simple but effective method is using a parity bit.
A parity bit? Okay, what's that? It sounds kind of mysterious.
It's not that mysterious. It's like adding an extra bit to each frame to act as a check.
At a check, like a safety net.
Exactly. The sender sets this parity bit to either a 0 or a 1 to make sure the total number of 1 bits in the frame is either even or odd.
Even or odd, I see. And how does that help?
Well, the receiver can then check this parity and immediately know if a single bit was flipped during transmission.
Oh, so it's like a built-in alarm system going off if something looks wrong.
Exactly. And for even more robust error detection, there are more complex techniques like the cyclic redundancy check or CRC.
CRC, so what does that do?
It can detect multiple bit errors. It's like having a superpowered detective examining your data.
Wow, that's pretty cool. So thanks to these error control mechanisms, we can enjoy streaming, gaming, downloading, all without worrying about data corruption.
That's right. Error control is essential for all those things. It keeps our downloads complete, our streams smooth, and our gaming lag-free.
It's all part of the magic of the data link layer.
Exactly. It's the unsung hero of reliable digital communication.
I'm starting to realize just how much work the data link layer is doing behind the scenes. It's like the invisible hand that keeps the internet running smoothly. But before we get too carried away with praise, let's talk about how the data link layer actually handles all those frames traveling across the network. We talked about their structure, but what about the process of sending them? Is it a free-for-all, or is there some method to the madness?
It's definitely not a free-for-all. There are very specific methods for controlling access to the shared medium, especially when multiple devices are trying to communicate at the same time.
Shared medium, so that means...
It means the same network cable or the same wireless frequency.
Ah, I see. So everyone's trying to use the same space.
Exactly. One common method, especially for Ethernet networks, is called CSMASD.
CLASD. Wait, didn't we talk about CSMA earlier?
We did. CSMA stands for Carrier Sense Multiple Access, and it's all about devices listening politely before transmitting to avoid collisions.
Right, like waiting your turn to speak.
Exactly. But CSMASD adds another layer of protection: collision detection.
Collision detection. So even with everyone listening, collisions can still happen.
They can. Imagine two devices starting to transmit at almost the same time. They both think the line is clear, but then bam, their signals collide.
Oh, that makes sense. It's like two people starting to talk at the same time, and then there's that awkward silence.
You got it. That's where the CD part of CSMACD comes in. When a collision happens, the devices can sense it, stop transmitting, and wait a random amount of time before trying again.
So it's like a built-in system for resolving awkward data conversations.
You could say that. It helps minimize those collisions and keeps things running smoothly.
It's brilliant. It's like they thought of everything. So that's how things work within the same network. But what happens when you need to send data across multiple networks, like across the internet? Do the same rules and addresses apply?
That's a great question, and it brings us to another key aspect of the data link layer: addressing. You're right. Sending data across the entire internet needs a different approach. Remember those source and destination addresses we talked about earlier, the ones in the frame header?
Yeah, like the to and from on our data envelopes.
Exactly. Those addresses are perfect within a single network. But when you're sending data across multiple networks, those local addresses won't make sense on other networks.
So it's like trying to deliver a letter using only a street address. You need a city, state, and zip code to get it across a wider area.
Right. Perfect analogy. So we need a global addressing system.
Okay, so how does that work? Does the data link layer have a solution for that too?
It gets a little help from the network layer. The network layer uses IP addresses, which are unique across the entire internet.
IP addresses, right. Every device needs a unique global identifier. But isn't there a bit of a language barrier here? The data link layer uses MAC addresses, those hardware identifiers, and it doesn't really speak IP address.
You hit the nail on the head. There's definitely a translation process, and that's where ARP comes in.
ARP, what's that stand for?
The Address Resolution Protocol. Think of it like a directory service for the internet.
A directory service, so like a phone book.
Exactly. Let's say a device wants to send data to another device on the same network. It knows the IP address, but it needs the corresponding MMA address to actually deliver the frame.
So it's like knowing someone's phone number, but you need their street address to send them a letter.
Exactly. So what does the device do? It sends out an ARP request, basically saying, hey, who has this IP address? Give me your MC address.
Oh, that's clever.
The device with that IP address then replies with its MMASE address.
It's like looking someone up in the phone book using their phone number.
Precisely. Once the sender has the right MC address, it can build the frame with all the right info and send the data on its way.
Wow, that's ingenious. ARP is working tirelessly behind the scenes, making sure our data gets to the right device. Like the ultimate internet translator.
Exactly. ARP is one of those essential mechanisms that we don't really think about, but without it, internet communication would just stop.
It's amazing how all these complex processes work together seamlessly, and we just take it for granted.
I know, right? It's incredible. The data link layer is so much more than just putting data in frames and sending it off.
It really is. There's error detection, collision avoidance, addressing resolution. It's like a whole symphony of processes working together.
It's a marvel of engineering. And we haven't even talked about some of the more advanced features like quality of service, where the data link layer can prioritize certain types of traffic.
Quality of service, so that's how they make sure our video streams don't get interrupted, right?
Exactly. It's all about making sure the most important data gets through first.
It seems like we could talk about the data link layer for hours.
We could. There's so much to explore.
But I think it's time to move on and explore the different technologies that actually operate at this layer. We've mentioned Ethernet a few times, but there's a whole world of other protocols out there, right?
Absolutely. Each with its own unique features and uses.
From the early days of Aloha to the world of Wi-Fi. I'm ready to hear those stories. Shall we take a detour into the history and evolution of data link layer technologies?
Let's do it. It's a fascinating journey.
Okay, so let's continue exploring these data link layer technologies. I'm really curious about those early innovations like Aloha. It's amazing how something from decades ago can still influence how we connect today.
Aloha was truly groundbreaking. Remember, it was designed to connect computers on different Hawaiian islands using radio signals.
Wow, using radio signals way back then. That's impressive.
It was a bold idea, for sure. And it introduced a very simple approach to data transmission. If you have data to send, just send it.
Wait, really? Just send it? No checking if anyone else is talking, no collision avoidance. That sounds like a recipe for disaster.
Well, the original Aloha protocol did have a lot of collisions, but the genius part was the introduction of random backoff.
Random backoff. What's that?
If a collision happened, devices would wait a random amount of time before trying to transmit again.
Oh, so it's like, oops, sorry, I'll try again later when it's hopefully less crowded.
Exactly. And that simple idea, along with its evolution into slotted Aloha, which divided time into slots for transmission, laid the groundwork for more sophisticated collision avoidance techniques like CSAP's MAID.
All right, CSM Cindy, we talked about that earlier. It's amazing how these early, seemingly simple ideas had such a big impact on how networking developed. Like a chain reaction of innovation. But tell me, are there any data link layer technologies that don't use collision avoidance at all? Are there situations where collisions just aren't a problem?
Absolutely. In some cases, collisions just aren't an issue. Take point-to-point connections, for example.
Point-to-point, so that's...
It's when you have a dedicated link between two devices. There's no need to share the medium, so no collisions.
Ah, okay. Like a private conversation line. No one else can butt in.
Exactly. So you can use simpler protocols in those situations. One example is HDLC.
HDLC, what does that stand for?
High-level data link control. It's used a lot in telecommunications and industrial control systems where reliability is super important.
So it's all about making sure the data gets through no matter what.
Precisely. It uses sequence numbers to keep track of the order of frames, acknowledgments to confirm delivery, and error checking codes to catch any corruption.
Wow, so it's like a triple check system?
You could say that. HDLC is the go-to protocol when data loss is simply not an option.
That makes sense. But what about modern wireless networks like Wi-Fi? Wi-Fi is everywhere these days. Does it use HDLC too?
Good question. Wi-Fi uses 802.11, and while it shares some similarities with HDLC, like using acknowledgments and sequence numbers, it has its own unique challenges.
Challenges? Like what?
Well, wireless communication relies on a shared medium, the airwaves. And that means it can be affected by interference and signal fading.
Right. It's like trying to have a conversation in a noisy room. Sometimes the message gets lost.
Exactly. So 802.11 has some clever tricks to deal with those problems.
Tricks? Like magic?
Well, not magic, but pretty close. It uses spread spectrum modulation, which spreads the signal over a wider frequency band to minimize interference.
Spread spectrum. Okay. And what else?
It also often uses multiple antennas to send and receive data.
Ah, multiple antennas. That's for better signal strength, right?
Exactly. It helps improve reliability. The main point here is that the data link layer is always evolving to keep up with new technologies and environments.
It's had to adapt from those early days of Aloha the complexity of Wi-Fi today.
Exactly. It's been an amazing journey of innovation.
It really is mind-boggling to think about everything happening behind the scenes every time we go online. It's like a hidden world of complexity we rarely notice.
I agree. The data link layer is one of the unsung heroes of our digital age.
It really is. It's the foundation that makes our connected world possible, making sure our data gets where it needs to go reliably and efficiently.
Without it, we wouldn't have the internet as we know it.
Well, after this deep dive, I think we can all give a virtual round of applause to the data link layer. It's been an amazing journey, and I feel like I have a much better understanding of this essential technology. Any final thoughts before we wrap up?
Just this. The next time you're streaming a movie, sending an email, or just browsing the web, take a moment to think about all the work happening at the data link layer.
It's the silent workhorse of the internet. It deserves our appreciation. Thanks for joining us on this deep dive into the data link layer. We hope you learned something new and interesting. Until next time, keep exploring.